We're going to look at an example of a two-proportion z-interval, which is covered in section 10.1 of the text. We're going to look at an AP problem that uses these concepts. A large company has two shifts, a day shift and a night shift. Parts produced by the two shifts must meet the same specifications. The manager of the company believes that there is a difference in the proportion of parts that were produced within specifications by the two shifts. To investigate this belief, random samples of parts, and notice I'm underlining some important things here, were produced on each of these shifts, were selected. For the day shift, 188 of its 200 parts met specifications. And I'm going to call this P hat day. For the night shift, 120 of its 200 selected parts met specifications, and I'm going to call this P hat night. Okay, so that's where P hat day and P hat night. Use a 96% confidence interval to estimate the difference in the proportions of parts produced within specifications by the two shifts. Okay, so we're going to start with part A, and then we'll go back and look at part B. Okay, so the state one is, what am I trying to do? Here's my parameter of interest. PD minus PN is the difference in population proportions of parts that meet specifications between the day shift and the night shift. I want to estimate that difference with 96% confidence. So for the conditions, one thing that is different than what we've done in the past is that I have two different groups now, two different random samples, so I have to check the conditions for each group separately. So first of all, I say random samples were taken from each shift, 200 each. 200 is less than 10% of all parts on each shift, okay, which seems reasonable. Or I would say there's at least 2,000 parts made on each shift. Okay, remember, on each shift is important, from each shift. Now I check the NP and NQ for each of those. Well, remember that N is 200. The proportion is 188 over 200. So if you multiply those together, you just get 188. So it's okay to just say the number of successes is 188. N times P, the proportion that's made on the day shift. So NPD, and actually this should be P hat, Q hat, because we are looking at sample proportions here. So NP hat D is 188 and Q hat D is 12. NP hat N is 180 and Q hat N is 20. All are greater than 10, so all the conditions are met for doing a Z interval. Now, going to our sheet here, our formula sheet, remember that a confidence interval is a statistic. So this comes from a sample, plus or minus a critical value. In this case, we'll be doing a Z critical value. We use T for means, times the standard deviation of the statistic. The standard deviation of the statistic for two proportions is this. Okay, so we're going to, we talked about this on our simulation, is that we have to use what we call the Pythagorean theorem of statistics. We take each individual sample proportion standard deviation, we square it, so that's why there's no square root around this part. We square that, we add them together, and then we take the square root of the whole thing. So we're adding variances. Okay, so if this is the standard deviation, P times 1 minus P over N is equal to the variance. Okay, it's the standard deviation squared equals the variance. Okay, just wanted to remind you of that from previous chapter. Okay, so back to here. Okay, so we have statistic times our Z critical value plus the standard error of the statistic. So that, in this case, the statistic is the difference in the two sample proportions. The Z value comes from doing an inverse norm. We're 96, this is our 96% confidence interval, so I'm looking for my cutoff value, my Z-score here. 98% of the data is below that Z-score, so I would do inverse norm of 0.98, which gives me 2.054. I can also use the table, which is very handy. If I go down to do the t-table, and this probability, the shaded probability, is what's on the table here. So if this is 96% here, then this would be 0.02 and 0.02. So notice where this is 0.02, the upper tail, that goes with a 96% confidence level, and I kind of cut some of the middle of the table out. If you go all the way down to the bottom, this was for T, critical values, which have degrees of freedom. But if you go to an infinite degrees of freedom, the T distribution becomes the normal distribution. And so I can use the infinite row here for my Z critical values. And there's the 2.054 that I would get using inverse normal on the calculator. So those are two alternate ways of finding that number. Okay, now then to find the standard error of the statistic, I would find the standard deviation squared for each one of these and then add them together and take the square root of the whole thing. Now I recommend at this point to go ahead and do the test on the calculator, or do the interval on the calculator. So let's look, I have 188 and 180 out of 200, so just check my values here. So I'm going to do menu, statistics, confidence intervals, to proportion Z interval. I'm going to put in 188 over 200 for day, 180 over 200 for night. I'm going to make this a 96% confidence interval and push OK, and there's my values. And I'm going to go back and talk about what we're going to do with those numbers now. So I have my P1, P-hat 1 and P-hat 2 are going to go right here. I already have my Z critical value that I've done. So notice this would be 0.94, 0.06 over 200 from this P-hat 1. P-hat 2, this is 0.9, 0.1 over 200. So this whole value right in here, the 2.0454 times all of this, should give me the margin of error. So you can double check that. This is equal to the margin of error, which is 0.055565 from down here. Okay, so this whole value right here is the margin of error. Here's the actual confidence, the lower and upper values of the confidence interval. So do I want to see this formula with the numbers filled in? Yes, I do. I definitely want to see that formula with the numbers filled in. So to conclude, we're going to interpret the interval. We are 96% confident as the interval from negative 0.156 to positive 0.0956 captures the true difference in the proportion of parts that meet specifications, day shift minus night shift. Now the second question asks, based only on this confidence interval, do you think that the difference in the proportions of parts produced within specifications by the two shifts is significantly different from 0? Justify your answer. Because 0 is in the interval, so here's our confidence interval right here, because 0 is in the interval, it is plausible that there is 0 difference between the two shifts, because remember, we're 96% confident that this interval captures the true population proportion. So the population proportion might be 0, or the difference might be 0, it might be positive, it might be negative. So basically we have inconclusive results here. So the interval does not provide statistical evidence of a significant difference. It could go either way, or it could be 0. So that's the idea. 0 is plausible as a difference because it's in the interval, so we can't reject that as a possibility. If you have any more questions, I highly recommend looking at the examples in the book of the same type of problem in section 10.1.